Okay, so good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheCS. Yeah? This afternoon, we are very happy to have Professor Francois Engelbrecht with us as a speaker. And let me briefly introduce to you Professor Engelbrecht. Francois is a distinguished professor of chematology at Wits, where he's also the director of the Global Change Institute, and he specialized in climate change model development and simulations related to the topic. So I won't say anything more about that because he will speak about the topic with much more proficiency than I have. Yeah? But he's essentially responsible for setting up a lot of climate change or local regional climate change modeling facilities, and he's also leading the development of the African-based Earth system model. Yeah, and recently he was also a lead author in the famous IPCC report on global warming. Yeah, and I'm sure in his talk he will mention those aspects as well. He's a member of several committees that you can read them in an announcement. I don't want to steal time from his talk. Yeah, but we are very happy to have this talk today, also because this year is the International Year for Basic Sciences for Sustainable Development, and climate change is one of the very hot topics. Excuse me the pun. Yeah? That we need to address in this setting. Yeah? And nobody is more expert than Professor Engelbrecht to give us a first introduction to this team in a NITheCS Colloquium. Yeah? So Francois, please, you're most than welcome to start sharing your screen, and we are really looking forward to your presentation. Thank you very much.
Thank you so much, Francesco, for this very kind introduction, and also the invitation to present to the NITheCS community. And also many thanks to Renee for all her efforts to set up this talk. So, okay, yeah, I'm starting to share my screen now. And let me just go to presentation mode.
Perfect.
Oh, connects, yeah.
We can see it clearly now. Thank you very much.
Wonderful. Okay, so we're in business. I'll just go off video while I'm talking. I'm here presenting from my house today. Afternoon, colleagues. I'm going to talk about this very big news. I think many of us in the computational community has taken note of over the last few years, over the last few days, namely the release of the first publicly available exascale computing system. I'll talk about in more details about that a bit later on. But yes, also in the climate sciences, things are changing rapidly as we approach the exascale, also in our field of work. So I want to talk today specifically about how advancing supercomputing capabilities are internationally changing the nature of climate modeling. And I also want to reflect on our position in South Africa in this respect. And I want to talk about how we can remain competitive in what we do in the absence of having one of the world's leading supercomputing systems. But we'll get through all of that systematically. Let me first just point out that something very special happened last year. The Nobel Prize in Physics was awarded to 3 scientists, and 2 of them were in fact pioneering climatologists. So there on the left-hand side of this of the pictures you can see there on the slide, you can see pictures of the very famous Professors Manabe and Hasselmann. So Professor Manabe was probably the first climate scientist to build a climate model capable to tell us something about the effects of fossil fuel burning on the climate system. He also did some other pioneering work about which I'm going to talk in the next slide. And Professor Hasselmann, well, he was one of the world's pioneering ocean modelers. And atmospheric and ocean models in combination, of course, are today's climate models, the so-called coupled climate models. So it was a wonderful honor, I think, to the field of climate modeling to be awarded the Nobel Prize in Physics last year. Often, of course, well, it is true that sometimes climate modeling is referred to as applied physics. But of course, in NITheCS, we know that the theoretical and the computational physics are all valued. But I think it was no coincidence that the award was made to these two pioneering climate modelers last year. It was also the year during which the Intergovernmental Panel on Climate Change released its assessment report 6. And in a way, this award said, it just reconfirmed climate science is solid science. And it is providing us with all the evidence we need to take responsible decisions in terms of mitigating climate change and also adapting to climate change. Now, relevant to my talk today is some of the other pioneering work that was done in the early years of Professor Manabe's career. And I've written a short summary there, which was part of the accolades that were said about him at the time of him being awarded or co-awarded the Nobel Prize in Physics. And he studied in his work also the vertical transport of air masses into the atmosphere. We call this convection, and it's something that I think all South Africans have seen, even those in Cape Town, namely a thunderstorm. So thunderstorms or convection are responsible for the transport of vast quantities of heat and moisture upwards into the atmosphere. But the problem is that in Professor Manabe's days, at least, it was not possible to resolve this fundamental process in climate models. So yes, and why is that? It's simply because of spatial resolution, of course. When we run climate models, even today, we typically run these models at the resolution of 100 kilometers in the horizontal. Let me show you the next slide. So that's an example of a certain type of grid system used in climate models. So the distance from one grid point to the next, as we discretize the atmosphere and the ocean into a number of discrete points in order to simulate the governing equations, that's about 100 kilometers in the horizontal. And that was the average resolution of models that participated last year in the big IPCC assessment report. So there's no way that small-scale processes such as thunderstorms, which have diameters of a few hundred meters or maybe a few kilometers at best, you just can't resolve such systems on a typical grid of a climate model. So Professor Manabe's work was about how to treat those processes statistically. And it became known as a field that until this day is very important for the field. It's called cumulus parameterization. That's the statistical representation of the process of convection in the atmosphere in climate models where the resolution is too low for the process to be resolved. Now, this situation is currently being changed by the advent of the world's first exascale computers. And I'll get to that. For now, I just want to say, for those who don't have the background, climate models are, of course, based on the laws of physics. So ocean and atmosphere models are nothing else but the laws of momentum, mass, and energy conservation applied to the ocean and the atmosphere. Of course, a climate model must also simulate the coupled exchanges, the feedback processes or the fluxes between the ocean and the atmosphere. So today's climate models are all coupled ocean atmosphere models. They also have representations of the land surface and of the cryosphere. So they've become truly Earth system models. They really try to represent all processes happening in the Earth system. In the Intergovernmental Panel on Climate Change reports, the standard operating procedure is to make use of many different climate models, so big ensembles of models, in order to also in that way describe the uncertainty range associated with projections of future climate change. As I've mentioned, the last two bullets there, we need parameterizations for processes that cannot be resolved. And cumulus parameterization remains today one of the biggest uncertainties in projections of future climate change. In Africa, it's regarded as the single biggest uncertainty in terms of understanding how future rainfall patterns will change. Because nobody has found a holy grail in terms of how to represent this fascinating process of convection statistically in the models. So a few more background slides before I go to our topic for today, namely the role of exascale computing in the computational climate sciences. This slide just a further bit of important background for those who are not climatologists in the audience today to understand how we generate projections of future climate change. There is one thing the Earth system model cannot do. It cannot simulate what we as humans are going to decide in terms of the climate change mitigation actions we want to take on the planet. For example, we may choose to follow the dark red curve on the graphic there on the left-hand side. And from our current emissions of about 40 gigatons of carbon dioxide per year into the atmosphere, we may decide to continue to develop the world's economy using fossil fuels. And that is then what we call a low mitigation future. And that, of course, have certain consequences in terms of climate change impact and further global warming. I'll show a few slides about these consequences in the next few slides. But we may also make a completely different decision. We may decide to aggressively implement the Paris Agreement on climate change. And that takes us to that light blue line on the graphic. You can see in that line, emissions start to drop immediately in the 2020s. And by the time that we reach the middle of the century, there's no further carbon dioxide emissions into the atmosphere. We call that net zero, the point of net zero emissions, or it's also known as carbon neutrality. You may have read about that. It's frequently being discussed, of course, in the media, in the general discourse in the last several years. So carbon dioxide is, of course, the most important greenhouse gas. There are other greenhouse gases that are also important, and you can see there scenarios into the future there on the right-hand side. So as climate modelers, we do not decide which of these scenarios is the most realistic. We provide all of these carbon dioxide and other greenhouse gas scenarios to the modeling system. And the climate model then projects the climate change that will follow from the continued release of greenhouse gas emissions into the atmosphere. And in that way, we can then, for a given mitigation scenario, obtain an idea of how the future may look like in terms of climate change impacts. And let me now just show a few examples to complete our background discussion. This is the most basic type of statistic you can then obtain from these model simulations. So let's look at the dark red line at the top first. That corresponds to a future where we continue to fuel the planet's economy using oil and coal. And you can see that in such a future, the level of global warming, which is depicted there on the y-axis, is projected to reach a value of somewhere between 4 and 5 degrees Celsius by the end of the century. Now, that is, of course, a a tremendous increase in the global average surface temperature of the planet that will have, I can only call it, devastating consequences. We can talk about some of those soon. On the other hand, the light blue line, you can see in that case, climate or global warming stabilizes at a value of somewhere between 1 and 2 degrees Celsius, the light blue line. So the IPCC made assessments of this future rate of global warming as a function of different mitigation scenarios, previous slide. And the report did make some startling conclusions. That was the report released in August last year. The first was that it is now more likely than not that we will exceed global warming of 1.5 degrees Celsius. I guess some members of the audience will know that as we meet today, we are sitting at a value of about 1.2 degrees Celsius. That's the current level of global warming. So the report has assessed that we have left the mitigation process for too long. And even if we follow that light blue line, the Paris Agreement type future, we've probably left the process too late. And we are now more likely than not to exceed 1.5 degrees Celsius of global warming. And that will probably, the time of exceedance will probably be the early 2030s. That's bad news. The good news is that under such a Paris Agreement type future, the chance is excellent that we can still restrict global warming to below 2 degrees Celsius. Every bit of global warming we can avoid means avoided impacts. One problem is that the science is currently indicating that the tipping point at which the Greenland ice sheet will may become unstable. That tipping point may well be somewhere between 1.5 and 2 degrees Celsius of global warming. So we may well be initiating a tremendous change in the Earth system that will commit future generations to many meters of sea level rise. But let me not get distracted too much in the background, because today I want to talk more about the computational aspects of this work. I'll just conclude by showing two more examples of the types of outputs that climate models generate. These are outputs from global climate models. From the IPCC, we are here just looking at the ensemble average of about 50 different models. And we are looking at different levels of global warming in figures A, B, C, and D. And with each of those are associated patterns of regional warming. And what you can see is that our region in Southern Africa is projected to warm up faster than almost any other location in the Southern Hemisphere. So we have a very strong climate change signal. 1.5 degrees Celsius level of global warming, as I've mentioned, currently it seems as if that's waiting for us in the early 2030s. Let's hope that we never reach levels of 3 or 4 degrees Celsius of global warming, because the science then tells us that we can expect in our region certain tipping points. Now, that's also because of the projected changes in the rainfall for our region. So in these graphs, you can see yellowish colors, that's a future drier, indicates drier conditions into the future. And the greenish colors indicate parts of the world that are becoming wetter. Now, most of the world is, of course, becoming wetter as the planet is warming. It's something we can already see. And it's simply because a warmer atmosphere can hold more water vapor, and storm systems, they become more intense. There's more energy available for them, and they tend to produce more rainfall. But certain parts of the world are affected negatively in terms of rainfall by changes in circulation. Our region is one of them. So our region is not only busy to become warmer at quite a rather drastic rate, it's also becoming drier. And that drying is projected to, of course, become worse as we move deeper and deeper into the future. So very last background slide, and I won't talk about these aspects today because I really want to talk about the computational aspects. But for the climatologists and those interested, I have listed there at the bottom a paper that summarizes most of the IPCC assessment report 6 findings for our region in terms of what the biggest risks are in terms of changes in the climate system. So we call these tipping points, unprecedented events that have never happened before, but that can occur in Southern Africa, even in the next 2 decades, in a world that continues to warm. So those are the 2nd to the 5th bullets that I've listed there. The possibility of a Gauteng Day 0 drought, multi-year droughts impacting on the cattle and the maize industry in Southern Africa. There is a point of collapse, the science tells us. More frequent heat waves directly impacting on human health and mortality. It's happening right now in the Northern Hemisphere. We are not exempt, unfortunately. And then in the eastern parts of South Africa, although rainfall totals are already decreasing in general over the last several decades, the number of extreme events are increasing. So the number of intense precipitation events are increasing. And the most important risk we need to think about is the possibility of a tropical cyclone, an intense one, category 4 hurricane or 5 hurricane, we can say, reaching as far south as Maputo or Richards Bay in a warmer world. So this is the type of information that we are obtaining from climate models. So where can we improve? Where are the big uncertainties, and how can exascale computing help us to take climate change modeling to a new level? Well, let's start to talk about this. With exascale computing systems, we are of course referring to systems capable of an exaflop. And I guess many people in this audience, or maybe everybody, will know that that means a billion double precision floating point operations, strictly speaking measured against the HP Lindpack benchmark, which is about solving 10 sets of linear equations. Of course, as a climatologist or climate modeler, I'm merely following these developments with great interest. I'm certainly not a specialist in building these types of machines. But what is important to realize is that computing architectures are rapidly changing. That's the important message for, I think, all of us working in our field. And with that, our numerical solution methods in our climate models are changing, and they are taking advantage of these rapid increases in computational capabilities. Now, a good example is the computing system of the European Center for Medium Range Weather Forecasting. There, the very last point. That's actually ECMWF. I made a typo there. Its plan is to roughly 5 years from now release a type of numerical weather prediction model never seen before on the planet. It will have a resolution of 3 kilometers in the horizontal. That means it will be quite capable of resolving aspects of convection. We say that the system will be convection permitting. So it will resolve aspects of thunderstorms, at least. And this system is set that it will have a mixture of CPUs and GPUs, but about 1 million cores. So that is the type of system that is currently being designed in the world's largest international numerical weather prediction centers. So this is the news. I'm sure many of you have also been I've also been following this news. The Hewlett-Packard Enterprise Frontier, hosted at the Oak Ridge Leadership Computing Facility, announced the news that the OLCF5 computing system is now available, and also that it has obtained 1.1 exaflop performance following the RMAX test. The cost of the system, looking at their website, it's about $600 million US. And it takes an incredible 21 megawatts to keep this computing system going. So many challenges now, of course, remain in terms of making these types of systems available in the climate sciences. The first is, of course, the mere costs of systems such as this. So as you can see, the current, the estimated cost of the frontier system was about $600 million US. The electricity requirements are also staggering. A typical EXA system is thought to bring electricity requirement of about 30 megawatts. And the costs associated with that is a staggering $12 million per year. The carbon footprint is also a staggering 100 megatons per year. For all of us working in the climate sciences, this is something, of course, we have to think about very carefully, because how can we simulate the future on a computing system that contributes to making the future even warmer? That's a real dilemma for us. And of course, in some countries, at least in the European Union, the Green New Deal determines that the data centers, the climate data centers, need to be carbon neutral by 2050. So how's this going to work? Of course, that 100 megaton per year estimate, that is, of course, if the electricity is generated by coal. There are other challenges. Of course, if you want to deploy such a system at such high resolution in the climate sciences, we should realize that it comes with tremendous data storage requirements. For example, a 10-day forecast that will be generated by this new ECMWF 3-kilometer resolution system with 192 levels in the vertical and with output being written 3 hourly, which is common in our field. Just 10 days of data generated on such a grid translates to about 0.5 petabytes of storage. Just think how that will quickly escalate when we run a climate model at this resolution for 100 years into the future. So storage is, of course, a real practical constraint. And then finally, there are still issues around performance scalability, specifically in terms of inter-node communication, and also the very different architectures of GPUs and CPUs, with the GPUs requiring very different data layouts. The performance tuning is notoriously difficult. My colleagues working in the field are telling me. So it is not so easy to build an exascale system that also scales very well across nodes and across cores. So, colleagues, how are we going to benefit from these developments in the global south? Well, here's some statistics from the top 500 list that I think we are all familiar with, but it remains striking to look at it. If we look at the current performance share across regions in the world for the current world top 500 systems, we can see that almost all of that capacity is to be found in North America, in Asia, and in the European Union, also including the UK. I think there's still now one African system in the top 500 list. And I remember Werner Janssen van Rensburg, director of CHPC research, he mentioned to me recently, if I remember correctly, that system is based in Morocco. So the tragedy of this slide is that the regions in the world most affected by climate change, the developing countries, including Africa, have the least compute available to help prepare them against the changes that are coming. So how are we responding at the Global Change Institute at Wits, and how should we be responding to these challenges in Africa? Well, it's important, I think, to develop African-based coupled ocean atmosphere models, or so-called Earth system models. There are many scientific reasons to do this, but there's also some political reasons. The case is often being made that it's a global north who has, of course, caused these problems of global warming and climate change. These major challenges humanity are facing. Now they use their climate modeling systems to decide what to do, and also to tell African countries how to respond. So there is political value in climate models being based in Africa and being run by Africa. But there's also wonderful domain expertise in Africa in terms of African convection, African thunderstorms, the African land surface and the regional oceans, and how they interact with climate. So there's a very strong scientific case to be made also for that domain expertise to be consolidated in an African-based modeling system. So at the Global Change Institute, we currently are building such an African-based modeling system. It uses a so-called Q-based grid. That's the modern way to do this. It's a grid that's almost uniform across the globe. It offers a range of computational advantages. And the existence of the system at Wits allows us to perform research on numerical methods and their scalability in the context of the realities of African supercomputing, but also in terms of this growing trend towards exascale computing reaching the climate sciences. So with this modeling system, of course, our main task is to project future climate change in Africa. And it's also to a very large extent about building a new cadre of postgraduate students, eventually young scientists, climate modelers based in Africa that will live and hopefully continue to work in Africa. And and I'm very happy to recognize the contributions of the National Research Foundation Earth System Science Research Program in really funding the first cohort of climate modeling students at Wits. The first intake was in 2019, and we now have 24 postgrads working in aspects of climate modeling and climate model statistics. So now towards the end of the talk, I would like to say a few words about what we can currently do in South Africa on our available high-performance computing systems, specifically the Lengau cluster of CHPC. And I want to make a statement of how we can contribute to this new type of modeling. We call this the convective-scale modeling that the ECMWF Center intends to do operationally at 3 kilometer resolution very soon using an exascale computing system. So how can we contribute to this field in South Africa? So firstly, let me point out that we can perform extensive simulation experiments on the CHPC as it stands. This is the current experiment we are on the verge of starting to run. Final testing has just been slowed down by the terrible spell of load shedding. But effectively, you can see that we are making use here of 10 coupled models, so-called coupled model intercomparison project phase 6 global models. And these are the IPCC type models, and we are taking the output and we are downscaling these models using our modeling system applied over Southern Africa only. So we say that we applied a model as a regional climate model over an area of interest. And in that regard, you can see that insert on the right-hand side, that zoomed in grid over Southern Africa. So currently, in our new experiment, which will be the biggest climate modeling experiment ever performed on African soil, we intend to downscale 10 of these coupled global climate models to 8-kilometer resolution over Southern Africa and similarly over East Africa for 3 different SSPs. And those are different mitigation scenarios, as the climatologists in the audience will know. So that's basically what's on the card. And this experiment will likely start somewhere in August. This is what I'm talking about. There you can see such a regional grid, providing 8-kilometer resolution across a large Southern African domain. And on the right-hand side, you can see some of the first test simulations. And you can see how an 8-kilometer resolution simulated rainfall field looks like. And you can see that it is successful in portraying many of the rainfall features of the Eastern Escarpment and also of the Cape Fold Mountains in the south. There's a zoomed in view, and this is the same type of experiment over an East African domain centered over Malawi. And here you can see that at 8-kilometer resolution, the modeling system is capable to simulate, for example, the very impressive lake breezes that develop specifically along the western shore of Lake Malawi. Now, what about the convective scale? So 8-kilometer resolution is still not sufficient to get a good grip on convection. We call that the so-called gray zone. Convection is only marginally resolved. Now at 3-kilometer resolution or at 1-kilometer resolution, one can really start to simulate some of the aspects of thunderstorm dynamics explicitly, specifically the updrafts and the downdrafts within thunderstorms. Now this is one of the largest growing research fields in climate modeling. As I've mentioned now already twice before, we do expect the first operational numerical weather prediction system that can do this type of simulation globally, appearing from ECMWF more or less 5 years from now. So there's no way that even on our Lengau cluster, of course, we are not even close to the point where we can perform such simulations on Lengau, but with very, very innovative capabilities of our model simulation system, namely the fact that it can run on a so-called stretch grid by applying the Schmidt transformation to a Q-based grid system on the sphere. We can set up very high resolution grids over very small areas. So currently, if we deploy about 1,000 cores on the Lengau cluster, we can generate simulations of 1-kilometer resolution over an area of about 200 by 200 square kilometers, or 40,000 square kilometers, over an area such as the Drakensberg within weeks. Now, this means that we can undertake research on the simulation of thunderstorms in this part of South Africa where the thunderstorms are most important, namely the Eastern Escarpment. And in this way, we can contribute to the study field of resolving convection explicitly in models. We can make a very important contribution by studying convection in, say, tropical Africa or along the Eastern Escarpment areas of Africa, where none of the international groups will have their focus. These are, of course, also areas where we have a competitive advantage in terms of radar systems measuring thunderstorm attributes, and our rainfall station data network, and also the upper air soundings that are being done at a few stations across the African continent. So that is a way to treat everybody to get to the convective scale without having an exascale computer. So this is the very last slide, and after that, I hope we have time for some discussion. What do we need from what do we need in terms of high performance computing in South Africa to be competitive? Well, let me just summarize before I try to give an answer. There's certainly a trend towards exascale computing. It will arrive first in numerical weather prediction and maybe a bit later on in global climate simulation. We've spoken about what these systems mean. They are characterized increasingly by CPU and GPU combinations. So we need to also develop the capability in the African climate modeling system to code our algorithms to run on these mixtures of CPUs and GPUs. That's a wonderful growing research field. It's still new enough for us to make a contribution. These systems are not only about compute. Typically, they are associated with about 250 petabytes of storage. The costs are excessive. We've spoken about that. The carbon footprint is a major problem for us working in the climate sciences. And in the EU already, there's a requirement of these types of systems to be carbon neutral by 2050. So for us to undertake research, climate modeling research in Africa that remain internationally significant, or we may even say potentially world leading if we do our job well, what do we need? Well, not all climate research is, of course, currently happening at the convective scale. That's the new frontier. But right now, the simulations I've shown you, the big ensembles that we will generate on the Lengau cluster, they will be the highest resolution simulations generated for Africa to date. And they will therefore have immense value in understanding African climate dynamics and also climate change impacts. These simulations, to really do something significant there, one needs in the order of 20 million core hours per year. And if you really want to do large ensembles of production runs, we need in the order of 43 million core hours per year. So those of the colleagues here that are working frequently on the Lengau cluster will know that this is within a reach, especially that 2 million core hour value is within reach on the current Lengau. But of course, we are all hoping that the next version of the CHPC cluster will be a near-term feature. Then we can do these types of experiments much easier and faster. Right now, the experiment I've described, this is a 1 year or 2 year simulation experiment I've described with those numbers of core hours. Then finally, by using stretch grids, we can work right at a convective scale. Because we have the competitive advantage in terms of observational systems and domain expertise in Africa. We can make a leading contribution to this aspect of convection resolving simulations in Africa. Finally, of course, I think where we can form partnerships to get access to supercomputers that are available internationally, while we wait for the next version of CHPC, we should, of course, pursue that partnership. We have had some successes at the Global Change Institute in getting access to some supercomputing system in Texas, and possibly also, we hope in the near future, to the Barcelona Supercomputing Center. So that can help, of course. But in the long run, it is my hope, and I'm sure it's the hope of many of you, that we will become more and more self-reliant in building African supercomputing systems in support of the climate sciences, but also in support of all the other areas of focus within NITheCS. Francesca, with that, I hand back to you. I apologize for my dog who has gotten excited when people started arriving home for the day, and I hope we have some time for questions.
Yeah, thank you very much, Francois, for a fascinating and scary talk at the same time, because let's hope that we get soon enough computational power to counteract what the worst case scenarios look like at the moment. Yeah?